Imagine you're holding a tennis ball in your hand. It feels light, harmless, ordinary. Now imagine that without changing its mass, you begin compressing it. You squeeze it smaller and smaller. First it becomes the size of a marble, then a pebble, then a grain of sand. Its weight has not changed. It still contains the same amount of matter. But something extraordinary happens as it shrinks. The gravitational pull at its surface becomes stronger and stronger. Eventually, if you compress it enough, the escape speed from its surface would exceed the speed of light. At that point, not even light could get away. You would have created what we call a black hole. This idea sounds dramatic, but the physics behind it is surprisingly simple. Gravity depends not only on how much mass something has, but also on how tightly that mass is packed together. The more compact the mass, the stronger the gravitational field at its surface. The Earth pulls on you with a steady force because its mass is spread out over thousands of kilometers. If Earth were compressed into a sphere about the size of a marble, its surface gravity would become so intense that nothing could escape from it. Not rockets, not particles, not even light. Now let's slow down and examine something subtle. When we say nothing can escape, we are not talking about a powerful suction force like a cosmic vacuum cleaner. We are talking about geometry. According to Einstein's theory of general relativity, gravity is not a force in the traditional sense. It is the curvature of space and time. Massive objects bend space-time, and other objects simply follow the curves. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet dips downward. If you roll a marble nearby, it spirals inward, not because the bowling ball is pulling it with an invisible rope, but because the surface itself is curved. That picture is only an analogy, but it helps. Now imagine pushing that bowling ball deeper and deeper until the dip becomes so steep that the rubber sheet forms a narrow funnel. At some point, the funnel becomes so deep that once the marble passes a certain boundary, every path leads downward. There is no route that climbs back out. That boundary is what we call the event horizon. It is not a physical surface. It is not made of matter. It is simply a limit in space-time. Beyond it, all possible future paths point inward. The reason black holes are so unsettling is not just that they trap things. It's that they redefine what direction means. Inside that boundary, moving forward in time inevitably means moving closer to the center. This is where black holes become far deadlier than the simple image of crushing gravity suggests. They are not just heavy objects. They are regions where the structure of space-time itself becomes so distorted that escape is no longer part of reality. That shift, from thinking about force to thinking about geometry, is the first step in understanding how extreme and how strange these objects truly are. Expanded to part 500 words and remove all narrator headings and brackets. Now let's move closer. Imagine you are floating in space far from any stars with a black hole ahead of you. From a distance, it doesn't look like a monster. In fact, if it is not actively feeding on nearby gas, it would be almost invisible. You would only notice it because of the way it bends light from background stars, like a warped lens in the sky. From far away, it behaves just like any other object with mass. If our sun were magically replaced by a black hole of exactly the same mass, Earth would continue orbiting almost normally. The gravitational pull at our distance would not change. This is important. Black holes are not cosmic vacuum cleaners sucking everything in. Their danger is local, not universal. But now imagine you fire your rockets and slowly drift closer. As you approach, something interesting begins to happen. The difference in gravity between your feet and your head grows. On Earth, that difference is tiny. It gently raises ocean tides. Near a black hole, that difference becomes enormous. Your feet feel a stronger pull than your head. The closer you get, the more dramatic the difference becomes. This stretching effect is called tidal force. If the black hole is small, say a few times the mass of the sun, the tidal forces near the event horizon would be catastrophic. You would not cross quietly. Long before reaching the boundary, your body would be stretched vertically and squeezed horizontally. Your spine would lengthen. Your internal organs would be pulled apart. Molecules would separate. Eventually, even atoms could be torn from each other. You would become a thin stream of particles falling inward. Physicists sometimes call this spaghettification, which sounds almost humorous. But the reality is not humorous at all. It is a precise consequence of gravity increasing rapidly over short distances. Now here is something counterintuitive. If the black hole is enormous, millions or billions of times the mass of the sun, the tidal forces at the event horizon might be surprisingly mild. You could cross the boundary without immediately noticing anything unusual. There would be no wall, no flash of light, no sudden jolt. From your own perspective, nothing dramatic marks the crossing. And yet, from that moment on, escape becomes impossible. This is what makes black holes conceptually deadly. The event horizon is not a physical barrier. It is a boundary defined by the structure of spacetime. Once inside, every possible future path leads toward the center. You can fire rockets, you can struggle, you can turn around. But all possible directions point inward in the same way that tomorrow always lies ahead in time. Think carefully about that. On Earth, you can choose your direction in space, left or right, forward or backward. But you cannot choose to move backward in time. Inside a black hole, moving toward the center becomes as inevitable as moving into the future. The real danger is not the crushing. It is the inevitability. And that inevitability is built into the geometry of reality itself. Expanded 3 part 500 words and remove all narrator headings and brackets. As you continue falling inward, something even stranger happens. To an observer far away, you never quite seem to cross the event horizon at all. Your image slows down. The light you emit becomes stretched to longer and longer wavelengths, shifting from visible light to infrared, to radio waves. You appear to freeze at the edge, fading and dimming until you effectively disappear. From their perspective, you are suspended at the boundary forever. But from your own perspective, nothing like that occurs. Your watch ticks normally. Your thoughts proceed as usual. You cross the event horizon in a finite amount of time without seeing anything special at that exact location, assuming the black hole is large enough that tidal forces there are gentle. This is not a trick. It is a consequence of how time flows differently in strong gravitational fields. Gravity does not only bend space, it bends time. The stronger the gravitational field, the slower time passes relative to distant observers. Near a black hole, this effect becomes extreme. To someone far away, your clock appears to run slower and slower as you approach the horizon. To you, their clock appears to run faster and faster. Two observers, two valid descriptions. Neither is privileged. Both are correct within their own frames of reference. This duality is deeply unsettling because we are used to thinking of time as universal. We imagine a single cosmic clock ticking everywhere in the same way. Black holes reveal that this intuition is wrong. Time is local. It depends on where you are and how you move. Now suppose you continue inward. Eventually, tidal forces grow without bound. No known material structure can withstand the increasing curvature of space-time. Even if you cross the horizon unharmed, the journey cannot continue indefinitely. According to classical general relativity, all paths lead to a singularity at the center, a region where density becomes infinite and the curvature of space-time becomes infinite as well. But infinity in physics is rarely a final answer. It usually signals that our theory has reached its limit. When equations predict infinite density, infinite curvature, infinite temperature, it often means we are applying them beyond the domain where they remain valid. General relativity is extraordinarily successful at describing large-scale gravity, but it does not include quantum effects. And near the singularity, quantum effects must matter. This is where our knowledge begins to fracture. We have two incredibly successful theories. General relativity describes gravity and the structure of space-time. Quantum mechanics describes the behavior of particles and fields at the smallest scales. Each works beautifully in its own domain. Yet inside a black hole, they demand to be used simultaneously, and they refuse to cooperate. The mathematics becomes inconsistent. Predictions break down. So what actually happens at the center? Does a true singularity exist? Does space-time tear apart? Does some unknown quantum gravitational effect prevent infinity from ever forming? We do not know. And that ignorance is not due to a lack of effort. It reflects the fact that black holes push physics to its conceptual edge. They are not merely distant astronomical curiosities. They are natural laboratories where the fundamental structure of reality is tested to destruction. Expanded forced part 500 words and remove all narrator headings and brackets. Now let's consider something even more unsettling than being stretched apart or crushed at the center. Imagine you throw a physical object into a black hole. A notebook filled with equations, drawings, memories written in ink. That notebook is not just matter. It contains information. The arrangement of molecules in the paper, the patterns of ink, the structure of the atoms, all of it encodes specific details. In ordinary physics, information is never truly destroyed. If you burn the notebook, the paper turns to ash and smoke. But in principle, if you could track every particle precisely, you could reconstruct what was written. The information becomes scrambled, dispersed, but not erased. This principle is deeply embedded in quantum mechanics. The equations that govern particles are reversible. If you know the exact state of a system now, you can calculate what it was before. But black holes seem to challenge this idea. If the notebook falls past the event horizon and eventually reaches the singularity, what happens to its information? From the outside, it appears lost forever. And here the story becomes even stranger. In the 1970s, Stephen Hawking showed that black holes are not completely black. Due to quantum effects near the event horizon, they emit a faint radiation, now called Hawking radiation. This radiation causes black holes to slowly lose mass and eventually evaporate over immense timescales. So imagine waiting long enough. The black hole radiates energy for billions or trillions of years and finally disappears. The notebook is gone. The black hole is gone. What remains is a faint bath of radiation drifting through space. The question is simple but profound. Does that radiation contain the information that was once in the notebook? Hawking's original calculation suggested no. The radiation seemed purely thermal, random, carrying no detailed information about what fell in. If that were true, information would be fundamentally destroyed. And if information can truly vanish from the universe, then quantum mechanics, our most precise theory, would need revision at a deep level. This puzzle is known as the black hole information paradox. It is not a minor technical issue. It strikes at the heart of whether the universe is fundamentally predictable. If information disappears, then the future cannot be fully determined even in principle from the present. A basic symmetry of physical law would fail. Over the decades, many physicists have argued that information must somehow escape, subtly encoded in correlations within Hawking radiation. Ideas from quantum gravity, string theory, and holography suggest that perhaps the information is not destroyed, but stored on the surface area of the black hole, not its volume. The mathematics hints that space-time itself may behave like a hologram, where the information about a region is encoded on its boundary. Notice how far we have come from the simple image of a collapsing star. Black holes force us to question whether space and time are fundamental or emergent. They blur the line between geometry and information. They suggest that reality at its deepest level may not be made of solid objects at all, but of relationships, correlations, and quantum entanglement. In that sense, black holes are deadlier than we imagined, not because they merely destroy matter, but because they threaten the logical structure we believe the universe obeys. Expanded fast part 500 words and remove all narrator, headings, and brackets. There is another layer to this story that makes black holes even more unsettling. We often imagine them as isolated objects, collapsed stars sitting quietly in distant galaxies. But in reality, black holes shape the structure of the universe on enormous scales. At the center of nearly every large galaxy, including our own Milky Way, there is a supermassive black hole containing millions or even billions of times the mass of the Sun. These objects are not rare accidents. They appear to be fundamental components of galactic architecture. Stars orbit them. Gas clouds spiral inward. Entire galactic cores seem organized around their presence. In some cases, when matter falls toward a supermassive black hole, it forms an accretion disk that heats up to extraordinary temperatures. Friction and magnetic fields accelerate particles to nearly the speed of light. Enormous jets of radiation shoot outward for thousands of light years, carving through interstellar space. These jets can regulate star formation, heating gas and preventing it from collapsing into new stars. So black holes are not merely destructive endpoints of stellar evolution. They are engines that influence cosmic evolution itself. Yet even here, something subtle emerges. The jets and radiation come not from inside the event horizon, but from matter outside it, still in the process of falling. Once matter crosses the horizon, it becomes causally disconnected from the rest of the universe. The violence we observe happens at the edge, not within. The most dramatic effects are produced just before the point of no return. This raises an interesting thought. The event horizon acts like a one-way membrane in space-time. Information, matter, and light can cross inward, but nothing classical can cross outward. It is as if nature has drawn a boundary where observation ends. We can measure the mass, the spin, and the electric charge of a black hole from the outside. Remarkably, those three quantities completely describe it in classical general relativity. This is sometimes summarized by the phrase, black holes have no hair. No matter what complex object formed the black hole, a star, a cloud, something chaotic, the external description becomes astonishingly simple. All the details disappear behind the horizon. Think about what that means. Complexity collapses into simplicity. The rich structure of matter is reduced to just a few numbers. It is as if the universe hides detail behind a curtain and presents only a minimal summary to the outside world. And yet, at the quantum level, we suspect that the details are not truly gone. They may be encoded in ways we barely understand. This tension between simplicity and hidden complexity makes black holes conceptually dangerous. They force us to confront the possibility that reality has layers we cannot directly access. When we look at the night sky, we see stars as points of light. We imagine space as mostly empty. But scattered throughout that darkness are regions where space-time folds so deeply inward that our best theories strain to describe them. Black holes are not just extreme objects. They are boundaries of knowledge embedded within the universe itself. Expand it 6 part 500 words and remove all narrator headings and brackets. Now let us step back and ask a more uncomfortable question. What if the very concept of a black hole is incomplete? Not wrong, but incomplete in the way Newton's gravity was incomplete before Einstein. For centuries, Newton's equations described planetary motion with extraordinary precision. They worked, yet they were not the final story. Einstein revealed that gravity was not a force acting across space, but the curvature of spacetime itself. The deeper explanation replaced the older one without discarding its usefulness. Black holes may be waiting for a similar conceptual revolution. When we describe an event horizon, we treat it as a smooth, well-defined boundary predicted by general relativity. If you fall freely, you should notice nothing special at that exact location. This idea is rooted in the equivalence principle, one of the foundations of Einstein's theory. It says that locally, free fall feels like weightlessness. Crossing the horizon of a large black hole should feel no different from drifting in empty space. But when we combine quantum mechanics with this picture, tension appears. Some physicists have proposed that the event horizon might not be smooth at all. Instead, it could be surrounded by intense quantum effects, a so-called firewall, that would instantly incinerate anything attempting to pass through. If that were true, then the equivalence principle would fail at the horizon. A cornerstone of relativity would crack. This is not a minor adjustment. It would mean that space-time behaves differently than Einstein predicted under extreme conditions. And the debate is not settled. The mathematics allows multiple possibilities, each preserving some principles while sacrificing others. We are forced to choose which parts of our understanding we trust most. There is also the idea that space-time itself may not be fundamental. Some modern approaches suggest that space-time emerges from deeper quantum relationships. In this view, geometry is not the base layer of reality. Instead, entanglement. Correlations between quantum systems might weave space-time together like threads in a fabric. If that is true, then a black hole could represent a place where those threads rearrange in extreme ways. Imagine discovering that what you thought was a solid sheet of metal is actually made of tiny interlocking rings. Under normal conditions, the surface appears smooth and continuous, but under extreme stress, the underlying structure becomes visible. Black holes might be regions where the hidden microstructure of space-time reveals itself. We struggle with these ideas because they violate intuition at every level. Our minds evolved to understand solid objects, flowing water, and falling stones. We did not evolve to visualize curved four-dimensional manifolds or quantum entanglement spanning cosmic distances. When physicists write equations describing these phenomena, they are manipulating symbols that represent realities no human has directly experienced. So when we ask what happens inside a black hole, we are really asking how far our theories can be trusted. We are probing the limits of language, mathematics, and imagination. Black holes are not merely distant dangers in space. They are mirrors reflecting the incompleteness of our understanding. And that may be the deepest sense in which they are dangerous. Expanded 7 part 500 words and remove all narrator headings and brackets. Let us now consider the ultimate fate of a black hole, because even these extreme objects are not eternal. According to quantum theory applied to curved spacetime, a black hole slowly loses mass through Hawking radiation. This process is unimaginably slow for large black holes. A stellar mass black hole would take far longer than the current age of the universe to evaporate completely. A supermassive black hole would last vastly longer still. But the mathematics suggest that, given enough time, even these giants fade away. Think about what that implies. A star forms, burns for millions or billions of years, collapses into a black hole, and then the black hole itself slowly radiates and disappears. The universe is not static. Even its most extreme structures are temporary. As a black hole radiates, it shrinks. And here another strange effect appears. The smaller it becomes, the hotter it gets. This is the opposite of most familiar objects. If you remove heat from a hot rock, it cools down. But a black hole losing mass grows hotter and radiates more intensely. In its final stages, it would release an enormous burst of energy before vanishing. What remains afterward? According to the simplest interpretation, nothing but radiation spreading outward. No solid core, no remnant. Just energy dispersed into space. But this returns us to the question of information. If the black hole completely evaporates, and if the radiation is truly random, then the detailed history of everything that fell inside would be erased from the universe. Entire stars, planets, perhaps even the atomic traces of life, reduced to thermal noise. Many physicists resist this conclusion. They argue that quantum mechanics forbids such erasure. Subtle correlations in the radiation must encode the missing information, even if extracting it would be practically impossible. In recent years, the calculations using quantum gravity models have suggested that information might indeed leak out gradually, hidden within delicate patterns in the outgoing radiation. Yet notice the conceptual shift. We began by thinking of black holes as massive gravitational traps. Now we are discussing them as thermodynamic systems with temperature and entropy. In fact, black holes have entropy proportional to the area of their event horizon. Not the volume, but the area. This simple mathematical fact hints that the fundamental description of nature might be two-dimensional at its deepest level, with the third dimension emerging from encoded information. That idea is radical. It suggests that the universe itself could function like a hologram, where the information describing a volume is stored on its boundary. Black holes provided the first serious clues pointing in this direction. So in the end, black holes are not merely cosmic hazards. They are crossroads where gravity, quantum mechanics, thermodynamics, and information theory collide. They compress not only matter, but ideas. They take our most reliable theories and force them into tension. They reveal that reality is layered, subtle, and far stranger than everyday experience suggests. When you look at the night sky and imagine a black hole lurking invisibly in the dark, you are not just picturing a region of strong gravity. You are contemplating a place where space and time bend, where information may be hidden, but not destroyed, and where the limits of human understanding are quietly exposed. And that realization changes how you see the universe.